Thank you. My name's Tony Klee, and I work for Dr. Peter Delfiat in the College of Optics and Photonics. And what I've been working on for the past few years has been building and characterizing a very particular type of laser system. And I would just like to talk for a few minutes about each of those two branches. So the type of laser that we build is very unique for a number of reasons. The first reason being that it's based on semiconductor devices, similar to what you might find in a laser pointer. And semiconductors are great because they're very energy efficient, and they're also very small and compact, and you can fit them into a wide variety of devices. One of the other outstanding characteristics of our lasers is that unlike a laser pointer where you just have red or green or one particular color, if you were to look at the output of our lasers, we actually have a very broad spectrum of colors or frequencies in the output. And if you were to look very closely, what you'd find is that they fall on a very evenly spaced grid, like teeth on a comb. And so we actually call this an optical frequency comb. And this has a broad range of applications, from ultra-precise optical clocks to sources for telecommunication networks. So now the other thing that I said I did was characterize these lasers. Light is, as we know, a electromagnetic wave, similar to microwaves or radio waves, but at a much higher frequency. Light oscillates at around 200 trillion times per second, and no detector on Earth can measure fluctuations at that speed. So you have to get creative about how to measure these sorts of waveforms. And there are a broad range of existing techniques already, but what I've been working on is a technique where basically we mix two of these optical frequency combs together and look at the interference pattern, and from that deduce some parameters about our laser. And just as a kind of analogy, if you've ever tuned a musical instrument or played with two tuning forks of slightly different frequencies, if you strike both of them at the same time, you'll hear this sort of warbling between the two. And what you're hearing is actually the difference in frequency between the two. You can do the same thing with light. You can take two laser beams of two different frequencies or colors, mix them together and detect, and you'll get an electrical signal at the difference frequency. And so we make use of this phenomenon to basically slow down light and be able to measure optical waveforms with very slow electronic detectors. So that's all the time I have, but please stop by my poster and ask me more questions. Thanks.